So in this problem, we have a block of a certain mass, and it's at rest on an incline of so many degrees above horizontal. Also, a so many Newton force is pulling on the mass down the ramp, and another force is pressing the mass into the surface. Find the normal force and the friction force on the mass. So there's our situation. Let's draw a free body diagram. There's the force pressing mass into surface, and there's the force down the ramp. We also have the weight, which must be resolved into a perpendicular to the surface component and a parallel to the surface component. You can imagine that if we had drawn the mg vector onto this free body diagram, you can see that it would go straight down to there. But that mg vector isn't very useful. mg cosine theta, as I've drawn it, and mg sine theta, now those are useful vectors. Okay, are there any other forces? Well, how about the normal force and the friction force? So let's write a Newton's second law equation for the forces in the perpendicular direction. That would be the normal force and the force that's pressing the mass into the surface and mg cosine theta. If I choose the normal force direction as being positive, then the force pressing the mass into the surface is negative, and you can see from the diagram that mg cosine theta is also negative, and that should equal the mass times the acceleration perpendicular to the surface. This mass is at rest, so it's not accelerating, which means since we're given the mass and we're given theta, and we know what g is, and we're given the force pressing the mass into the surface, we should be able to solve this one for the normal force. And there's our answer for the normal force. Now let's look in the other direction. If we sum the forces parallel to the surface, if I choose down the plane to be positive, then I've got mg sine theta plus the force down the ramp minus friction, because friction goes the other way, and that equals the mass times the acceleration parallel to the surface. Again, this mass is at rest, so it's not accelerating, so the right side turns into 0, and I should be able to solve that for the friction force. We're given the mass, we know g, we know the angle theta, and we know the force down the ramp, and if we do a little algebra, there's our static friction force. Let's try another one. Now we have a force that acts downward along a so many degree inclined plane on a so many kilogram mass. The force is parallel to the plane, the coefficient of kinetic friction is given, and the mass is already moving. So we don't know how fast it's moving, but we do know that it's moving, and we want to find the rate at which its velocity is changing, namely its acceleration. So let's draw a free body diagram. There's the applied force. We're told that it's parallel to the plane. If we were to draw the weight of this mass, we would draw mg straight down. But that is not a useful force because it's neither parallel nor perpendicular to the plane. So I'm going to resolve it into its components. Notice that whenever we tip to tail mg cosine theta and mg sine theta, tip to tail, those should have the same effect as mg straight down. We also have a normal force. There's a kinetic friction force. Kinetic friction is always equal to the coefficient of kinetic friction times the normal force. And I think we're ready to go. So let's write a Newton's second law equation. We'll sum the forces in the perpendicular direction first. Generally a good idea to do the perpendicular direction first. In the perpendicular direction, this mass is not going to be accelerating. We can solve this for the normal force, since we know the mass, and we know g, and we know the angle. That's going to come in useful because, as you can see on the right here of this free body diagram, we're going to need that normal force. So if we can calculate it, that's going to help us in solving this second Newton's law equation. I'm going to choose down the plane as positive. So mg sine theta is positive, the applied force is positive, friction force is negative, and that should equal the mass times the acceleration parallel to the surface. We're looking for that acceleration. Again, we know the mass, we know g, we know the angle, we're given the applied force, we're given the coefficient of friction, and in the first step we calculated Fn. And of course we know the mass again. And there we go. Solve that algebraically for the acceleration, plug the numbers in when we're given them, we'll be done. We're nearing the end of our no numbers Newton's second law problem lessons. Here we ran into cases with a mass on an incline. As always, it is convenient to resolve forces into parallel and perpendicular components. For a mass on an incline at theta degrees, Fw perpendicular is equal to mg cosine theta, and Fw parallel is equal to mg sine theta. And you can see that in the diagram on the right.